All right, everyone, welcome. Today, we're diving into one of the most important ideas in all of physics, Planck's quantum theory. Seriously, this is the theory that completely flipped the script on how we understand energy, light, and pretty much the fabric of reality itself.
For the longest time, physicists thought about energy like a smooth, continuous ramp. You could have any amount you wanted, a little bit, a whole lot, or literally any value in between. But then Max Planck came along with this wild idea. He said energy is actually more like a staircase. It only exists in specific, separate steps. You can be on step 1 or step 2, but you can never, ever be floating somewhere in the middle.
So you have to ask, right? Why? Why make things so much more complicated? The smooth ramp idea seems so simple, so intuitive. What problem was so massive that it forced scientists to completely throw out the old playbook?
Well, the thing is, that old, classical picture of the world had a huge flaw, and the evidence was piling up so high it was just impossible to ignore anymore.
Okay, so here's the problem in a nutshell. When physicists ran experiments, especially ones involving heat and light, the numbers they were getting just didn't add up. The results completely contradicted what the classical wave theory predicted. Imagine you have this map that you know is perfect, but it keeps leading you to the wrong place. Eventually, you have to admit, something's fundamentally wrong with the map itself.
And this is where our hero, the German physicist Max Planck, enters the picture. Back in 1900, he proposed a solution so bold, so completely against all intuition, that it didn't just solve the problem. Oh no, it literally kicked off the entire quantum revolution and changed physics forever.
So what was this big idea? At its core, it's this. Energy isn't some continuous flow. It's bought and sold, if you will, in tiny individual packets. Each one is a self-contained little bundle of energy, and the universe only deals in whole packets, no fractions, no change.
And Planck gave this smallest possible packet of energy a name, a quantum. Just a few years later, a young physicist you might have heard of, Albert Einstein, took this idea and ran with it. He suggested that light itself is made of these particles, which he famously named photons. So yeah, every time you see light, you're literally being showered by countless tiny energy packets.
Okay, so if energy comes in these little packets, there has to be rules, right? How does this whole new quantum world actually work? Well, it turns out the first rule is surprisingly straightforward.
So get this, the amount of energy packed into a single photon isn't random at all. It's directly tied to its frequency. Think about it like this. A high-frequency photon, say from a blue light, carries a lot of energy. A low-frequency photon, like from a red light, has less energy. It's a simple, direct, predictable relationship.
And Planck boiled this whole relationship down into one of the most famous equations in all of physics, E equals h nu. In this equation, E is the energy of that one photon, nu is the frequency of the light, and h is kind of the magic number that connects them both. So that h is what we call Planck's constant. And just look at that number. It is so unbelievably tiny. You can think of this number as the fundamental pixel size of our universe. It defines the height of every single one of those energy steps, and its microscopic value is exactly why we don't notice this quantum staircase in our big, everyday world.
And its tiny number leads to the biggest, most important rule of the quantum world, the all-or-nothing rule. An atom can absorb or spit out one quantum of energy. That's h nu. It can handle 2 quanta, or 3, or any whole number you can think of. But here's the thing it can never do. It can't deal in fractions. There is no such thing as absorbing 1.5 quanta. It's always a whole packet or nothing at all.
Okay, let's do a quick recap of the key ideas here, because this is important. First, one photon is the same thing as one quantum of light energy. Simple enough. Second, you'll sometimes hear scientists talk about an Einstein of energy. That's just a gigantic bundle of photons, specifically a mole of them, which is a number so big it's hard to even imagine. And finally, because a light's frequency is locked to its wavelength, you'll often see Planck's equation written a little differently, relating energy directly to wavelength, or lambda.
I mean, it is really, really hard to overstate how big of a deal this was. Planck wasn't just fixing a small crack in physics. He accidentally stumbled upon a door to a completely new reality, the quantum world. So, if there's one thing you take away from all this, it's this profound shift in thinking. The universe, at its most fundamental level, isn't a smooth, continuous ramp. It's a series of distinct, countable steps. In a way, energy is pixelated.
And that leaves us with a really mind-bending question to chew on. If something as basic as energy comes in little chunks, what else does? Could space itself be made of tiny pixels? Could time tick forward in indivisible little moments? That is the rabbit hole Planck's theory threw open. And believe me, scientists are still exploring its depths to this very day. Thanks for joining me.